Second last talk.
Excuse me. Sorry.
The floor for the next hour.
Thank you very much. Right, so there's the title page, and yeah. So yes, I'm at Northumbria University. I'm retired, actually, but I'm still around in my dotage. Right, title. Bit of a challenging title. It's it's a big leap from where we've got in previous category theory applications. But since some of the category theory applications are working in the real world now, like Bitcoin, which I'm going to come along to later, I think it definitely shows promise. So let's just see how you might tackle a much more ambitious project with category theory. I make some acknowledgements. Michael Heather is well known to most people here, and we had a week on the Azores, the Whitehead Conference, at the end of July, which was very rewarding. So Michael Heather is a physicist, of course, so keeps me on the right line. Michael Brockway is, works at Northumbria University as a lecturer. He did his category theory MSc under Goldblatt, so I go to him for some advice on the actual theory. And I have also consulted some members of the Royal Northern Sinfonia at Sage Gateshead for exactly how they manage the performing, just as a check. Doesn't make me an expert in music, and there may be different experiences, subjective to some extent. But so I thank all those. Now I make the usual disclaimer that all misconceptions are my responsibility, not anyone else's. So this is the abstract, really. Yes, testing application for the Cartesian monad. Monad is process in category theory. So basically we have two strands. We have the topos, which we use for the data structure, and the monad, which we use for the process. I'm going to describe those in detail. And you can, obviously, one reason why I chose music, you talk about musical compositions, and the monad composition is one of the hot topics in computing science at the moment. So there is a link there. And the monad also has some very interesting features in its use in transactions. It looks forward and backwards, and the comonad looks backwards and forwards. You have a lot of backwards and forwards anticipation and reflection in the monad-comonad structure. So it looks interesting for this sort of application. Yeah, I'm not going down to the physical characteristics of the notes. That doesn't mean I can't. I'm not chickening out. It would be quite possible to have a notation actually included in a category. It's just that I haven't got time to do that. But that would be one of the obvious things to do. And obviously, when I talk about scores, they could be digital. They could be quite a range of different approaches. Cartesian monad is a monad that applies to a product. So that's a product of objects, and of course when you get a musical performance, it's, unless you're playing a single note, it's always a product. So it will be Cartesian. So the monad's process handling dynamic aspects, and the category upon which the monad operates will be a topos. And there you can put the players, the score, and the venue together with the relations between them. So this would be your musical program, in effect, or something like that. Plus the manuscripts that, if you're one of those who like to go into a performance and follow the performance on a score. So that's the basic idea. Topos is your database, in effect. But the topos is far from totally static. It can be very flexible, the way it's handling relationships. I'm not assuming any particular musical genre, though I'm actually going to deal with a classical orchestra, but there may have to be some adaptations if you've got a long way from a classical score, but I'm not trying to fix it to any particular genre. And this is the exciting thing in computing science, that functional programming languages like Haskell and Scala now include the monad and categories and functors as constructions. And so this means that having formulated something, you can actually implement it in the functional programming language. So category theory has come really quite a long way in the last few years on the strength of this implementation. I think what I produced today, I'm not suggesting that's going to be implemented. Right, so let's start off with the topos. That's a structural data type based on the Cartesian closed category. These are the categories we tend to use in information systems. So I should have added to my thanks to Lou for introducing categories earlier today, but I'm really going to talk about more these types of structures, categories like pullbacks and things like that, showing relationships. In information systems, everything is based on relationships between different types of data. And you get the relationship for a product. So if you multiply A times B, that opens up a relationship between A and B. And you can then specify a context, and you can get the relationship between A and B in that particular context. Topos is called topos because it's closed at the top. So if you imagine all the arrows all converge at the top. And there aren't two tops, there's only one top. Whether you have a bottom or not is argued about a bit more, but there's always a top, and Michael Heather certainly says it's always open at the bottom, and that means if you close it at the bottom, you've closed world assumption, and you're into a Boolean world. So keep it open at the bottom. It has connectivity between all the objects, has an internal logic, which is the lambda calculus, identity, and you can interchange levels. So you can take a structure and you can put objects into the structure if you want to, or you can replace all those objects by categories. So you have a lot of flexibility in what you actually put in. Pure mathematicians, there's about 20 different types of topos, and so generally if you start talking to pure mathematicians, they immediately say, what sort of topos are you using? Or they say, I don't think yours fits any of the types of topos, or something like that, which is a bit dispiriting, I must say. If we add to this Cartesian closed category a sub-object classifier, which is just a way of searching, internal logic of heighting, which is intuitionistic, and reflective subtopos, then we get the topos. So all our structures are basically topos. That's our basic building block. So I'm going to give some examples, and the first one is student marks. These are things we've done before. 1 square. Then I'm going to do bank transactions, which is the area where the category theory has been successful through blockchain. I'm going to do a simple pullback 1 square, a pasted pullback with 2 squares, and then another pasted pullback with 4 squares. So, but this is all data structure diagrams, and you've done entity relationship diagrams, these sorts of things. So that's what we're going to do. Right, so this is a pullback. This is the basic building block of a topos. This is the relationship of students, that's the S there, over M, that's down there, in the context of G. So this gives the actual students and who've got marks with their particular grade. And this adjointness, which holds across here, you've got 3 functors there. These are the standard logic operators. So that's the existential quantifier, that's the universal quantifier, and delta is a clever beast that picks out pairs of S and M that are related from this right-hand side. Category theory purists never make it easy, because you know you've got there, these are inclusion arrows, iota, there, I left and I right. And S and M aren't actually included in that G, but S and M must be there, because otherwise you can't include S on that, in that right-hand part without S actually being present. So,
could you just walk us through this, because this is very confusing.
Yeah.
Well, yes. What does it mean?
These are projections.
What does that mean?
That is a projection left, so that takes the left-hand side of the product and puts it onto S there. So that's a projection of part of the product onto an object.
And can you sort of express that in real world terms?
Think of the things on the horizontal line as factors in the product, and the thing at the top is the product. They're maps from the product into the factors, into anything which factors into that product.
Yeah, delta is the critical thing. Delta is taking pairs of S and M in this right-hand side and mapping them onto a product here.
Well, yeah, but are you talking about abstract operations with that structure, or
No.
or
It's a universal logic gate.
Oh, I see. So you're not modifying the thing that the arrow points at.
No, the existential quantifier will take what this S times GM and map it onto the S plus M plus G on the right hand side.
Probably a very simple way of making this clear would just be, instead of jumping in and talking about logic gates or trying to relate this immediately to the applications in musicology, would just be to take the example of the category of sets, where this becomes immediately apparent, because you're just simply talking about set theoretic product of any two objects, and it's just a way of representing geometrically the maps from any product into its factors.
So as I think about that, this is circles with points in them, and the points match with one another in one way or another.
That would be an example.
Okay.
Yes, it could be.
So it's a kind of mapping.
So in relational database operations, the pi is a projection.
Yeah.
The iota is an inclusion, that's saying it's included on that side. And the S times M, that's a join when you go from G to S times M in context of G. That's actually forming a join. And the universal one, it actually acts as a universal quantifier for all.
So that's a total mapping from every element from the left-hand side to the right side?
No, that will find everything in G for a particular time. That's really finding everything. So
Could you explain the notion? I'm sorry, because I don't have any background at all in music theory. What student marks by grade? This is simply what marks that people get on.
Yeah, that would be the names of the students. Those would be the marks they get, and this will be a grade awarded.
Oh, I see.
Might be
So it's nothing specifically to do with music. It just could be any.
Oh no, this is just. I'm just introducing.
Okay. I was a little bit confused because you jumped in and started talking about specifically applications of this to music theory, and now we're back in a much more general illustration.
I'm giving some examples of pullbacks.
Okay, fine, got it.
Yeah, okay.
These are just general examples of pullbacks, push-outs.
I mean, I can just skip through to the music example, but I think I'd like to deal with the banking example as well.
Yes, that would be interesting.
Yeah. So the point of those arrows across the thing is that they give you the facilities for SQL and any Google type query language or anything like that. It opens it up to querying. That's the basic idea. Okay.
So then what's the difference between this and an ordinary entity relationship diagram?
That's a very good question. I'll go back to that. An entity relationship diagram is just symbols. It is drawing symbols.
Yeah.
These are categorical types. And so, like here, where you've got this pi L onto S, you've got all the features of the entity relationship diagram there in the mapping. So, for instance, if you project these onto S and you have some S left unassigned, then you know that S, it's not mandatory for the students to be assigned a mark and a grade. So all the features of the entity relationship are contained there, but they're within the typing of the category of typing.
So you've got some rules built into the diagram.
That's exactly right. Yes, you've got all the rules are built into the diagram through the category fitting. So this is much closer to if you have the associated types, like whether it's monomorphic, that's ejective, or subjective means onto. You've got all those properties are in that diagram.
I think you meant to say surjective, didn't you?
Yes.
So, sorry, surjective. What did I say?
You said subjective.
Surjective, yeah. So all the classical set theoretic rules that you put into a data structure diagram are actually contained in that.
All right.
So it makes it much closer to an implementation than in an entity relationship diagram. Okay, I have got some explanation on there. I think they've really done that. Yeah, I think I'll leave these because...
I mean, you've got existential and universal quantification in there.
Yeah.
That's presumed just as an illustration of the notion of adjointness.
Yes.
I mean, existential and existential universal quantifiers are famously left and right adjoint to substitution. But of course, there's one example of the notion of adjoint functors. I mean, I think it's a little bit confusing here because you seem to think
that's a specific case of the student database.
Yeah.
Explain what
Delta is right adjoint to the existential.
Yes, but in the case of this example of in the case of the example of bank transactions, there must mean something much more concrete. Perhaps it would help if you could just say what the existential universal quantifier notation is doing in the case of the bank transactions.
Yeah, well the delta, over this side you will have P plus A plus T, right?
Which is, I'm so sorry, can you define?
P is procedure, A is account, and T is transactions.
Right, okay, so you've got a triple consisting of the account,
So you've got P plus A
account.
plus T on the right-hand side, and delta will take pairs of P and A that actually exist in the real world.
That would be individual transactions on a bank.
Yes, that's the individual transaction. That's the pair of procedure and account that is involved in that transaction.
Right, okay. That makes
sense. So this is the real world. Procedure is...
The account is a certain person's account or business account.
Yeah, this will be someone's account. That will be some standard bank procedure like deposit, withdraw, something like that. And transaction will be the combination of the two. That's actually...
It'll be the way that the status account, the balance in the account is transformed by that transaction.
Do the arrows going in opposite directions undoing each other?
Sorry?
Do they undo the arrows in the opposite directions? Undo
No, I perhaps shouldn't have put all those on. Those are just, they're really to show if you want to do a complete data structuring, you need to look at all these relationships that occur on the diagram.
What are the relationships again? What is pi?
Well, like pi L is projection left of that onto P, and A is the projection right from there onto there.
Okay.
And pi R star is the inverse of that. That's the basic.
The subtle point about adjoint functors being that precisely that they don't exactly undo one another.
No, oh no.
That's the whole point. They don't quite. They come very close to, but they don't actually undo.
They are logic gates, these.
Yeah.
Yes, logical operators. That, so they're not actually... Yeah, so perhaps that is... I mean, you often see this written by category theory people, but the arrows have subtly different purposes. It's an overloading of the arrow symbol. So this is logic here.
In the case of the bank transactions, which I think everybody in this room, I'm sure, understands the simple notion of a bank transaction, what it does to your bank balance. I'm afraid I still don't understand what the existential universal quantifiers symbolise in that context.
They would enable you to make you've got P plus A plus T over here.
Yes. That's the triple consisting of the transaction,
that's
the account, and
of P plus A plus T. And so you would be able to, if you've got that information, you'll have much more information over there than you have on the left-hand side.
Right, that's why you need...
just a pair. Right. On the right-hand side, you've really got everything. You've got P plus A plus T, and you may have further information, all held in the sum.
Right. Okay, now I begin to see what the adjunction is.
So the existential is like an SQL command or database command, which says, given this this actual transaction that occurred, can you give me the person's name and their address and all sorts of other information that is available?
And in general, the answer to that would be no.
Well, the bank will want it if they want to send you a letter.
Well, I see. Well, yes, but you need to know. Okay.
Yeah.
But
so the right-hand side contains all the information summed together by very subtle, the difference between plus and times. Times means an explicit relationship. So that is like you made a deposit into account 1 and the transaction number is 26. The right-hand side, the plus, the information is implicitly related. So if you've got, say, you've got the name of the account and some further information on it, that further information will be held on the right-hand side. Go back to the student example.
Yes.
You've got the student number. If that determines student name and that determines student address, those two are related implicitly, student name and student address, but not explicitly. And in a relational database, you would write it as student ID with the key and student name and student address as other properties.
So is it like a one-to-many?
Yes, you can have a
Yeah,
one-to-many,
ones.
but the plus is implicitly related. The times is explicitly related. So there's quite a difference. But that's of course if you want to get into push-outs and pull-backs, that's the push-out side, the plus side. So you have this.
You haven't written a plus there.
Now this is, whether I should or not, category theory people don't, but I think it would make it a lot easier if I wrote P plus A plus T there.
Right. Yeah.
And it probably contains other information as well. Yeah. So I think, yes, I agree that the way things are written is not always very clear. So this would be a single relation. Yes, I've got some further information in that on the thing. So actually those are, I've got these as categories. So they can contain objects. So each of these categories, there are 4 categories there, they can each contain objects.
The categories are P, T, A, and
Yeah.
pair. Okay.
Yeah, they're the 4
And the
categories.
nodes.
And so that makes pi L and iota functors, because they are mapping between categories.
Okay.
Yeah. It's a matter of taste which way you do it, but if you define them as objects, then it's
Actually, that diagram you just showed, I think, was a great deal more clarifying and informative.
Yeah.
About that for a moment.
Well, that's showing a decomposition of category S.
Yes.
So what S actually contains underneath is this relationship Doolittle diagram, which goes from times into a plus on the right-hand side.
When you say decomposition, do you mean the inverse of?
No, it's actually what category S is in terms of objects.
Oh, in terms of the actual.
Yeah, so I've now switched to objects.
Yeah.
Okay.
Yeah. I think I should have I decided not to show that one. So this is just showing how you might represent some of the data for category S. So these so that category S there is that Doolittle diagram I showed later.
The whole thing is S.
Yeah, so that's actually a category containing those objects.
That whole thing gets subsumed in that S.
So that whole category S has been represented by that, another pullback square.
So that's the thing you sometimes do is the rectangles next to each other.
Yeah, so everything's pullback squares, I think, in this, which I agree is probably, it takes a bit of getting used to. Okay, so, done that one. Right, so we've done that. So this gives you a very simple way to relate bank transactions to an account. But you can go on and you can paste these diagrams together. Now, don't want to worry too much about these, but you've got this square. This is a square we've had already, PB1, and I'm now pasting another square onto it, PB2, where I'm putting on the user of the account. So there's a new relation coming here, which is of the user and this P times TA. That's the pullback we've already defined. And I'm now using that pullback to put it into another relationship with the account. Now, I suppose I have to apologise for doing this because most books show you clear this, they just show you one pullback. But if you're going to do real applications, you've got to get many pullbacks linked together. The world just is complicated. And so you can do these pullbacks like this, and you can go on pasting forever if you want. So, because you can't, like an entity relationship diagram, you can't just model the world with two entities and one relationship. You generally have 15, 20 entity types, even in a fairly simple application, and perhaps 20 relationships. So that's why I'm showing these things, to show it's standard category theory textbook, the way you paste them, and you can go on pasting, but there's a rule about it which is very common in category theory. You can paste a structure together, but every square in the structure you get has to be a valid pullback. So you can't mix up squares which are not pullbacks. So this is how it's normally written in, if you paste a square in a textbook. I do it this way because it tends to go on up. So this shows the relationship of the transactions by procedure and account with user in the context of the account. So it's actually building up a relationship structure.
So a pullback is a join.
Pullback is joined.
A pullback is a join.
The join is effectively that line there. Well, I've equated the right projection of the pullback 1 with the left inclusion of pullback 2. So you've got a common arrow in the two pullbacks, and so you paste along those.
So, but just being really concrete, I mean, we are talking about databases here. What is the pullback in terms of what?
The pullback is one relationship.
Is this a relational algebra?
The relational algebra is the extension quantifiers, the existential quantifier and the universal quantifier.
So, a relationship between
two entity types,
yes,
so they'd be category types. Yes, that's based over in a context with a third object or category.
So you would, I mean, in a database,
yeah,
you would have a primary key in each of those
yes,
tables, and you would do a join on the primary key.
That's right.
So is that the pullback?
Yes. The left-hand side is typically the key.
All right.
I think it's always the key.
All right.
So
I'm wondering why we need all this, because actually, I mean, it could be much more simply explained by not going near this stuff. Can't it?
No.
Well, it depends what you're familiar with.
Well, I wouldn't start here.
Maybe not with bank transactions. It might conceivably be that when you're coming to musicology, there are applications here which couldn't be handled by the database.
It's formulaic. You know, it's not. You don't have to think about each one. If you go back to this is the independent variable.
Yeah.
And this is the dependent variable. So this is the one that changes less. That's the basic one in the relationship. So if you like in a relational database, that's just one relation would be on P, another relation would be on A, and then you would have a link relation which contains your PAT. That's basically. You might say, well, why don't we just do it in entity relationship diagrams?
Yeah.
But entity relation diagrams are just symbolic. They don't contain all the typing information. You have to do that with labels.
Yeah, but they're very easy to understand. That's all. I mean.
Well, isn't the problem there that I mean, I'm maybe groping here myself, but isn't the problem there, and I understand this is part of the payoff for this approach, you're saying that the point is in real-world examples you may have multiple pullbacks.
Yeah.
And of course in the typical kind of mathematical example of category theoretic diagrams, because you're dealing with isomorphic structures, it isn't necessary to distinguish between those different pullbacks. You've just got one single kind of structurally defined pullback. But in these real-world examples, you want to be able, and suppose there is a transaction on the same account in the same day, which is for exactly the same sum and in other respects is identical to another transaction, except that it's entered by another payee, you know. So that's important information, which is only tracked by the distinction in the pullbacks here.
Yes.
Well, and that wouldn't be tracked, at least I can't immediately see how that would be tracked by, if one was simply doing this in terms of
By time of transaction?
Yes, but then again, you've got to enter that as a variable, haven't you? And again, even there could be two transactions which took place at the very same moment. And,
With far less probability.
well, yes, but still, but the point is, it's a perfectly, it's a logical possibility, and you would still need to be able to distinguish who the payee was, the payer and the payee were in the case of those two transactions. So I mean, I'm just trying to think of motivations for why you would need all of this machinery.
But if you're going to apply the monad, then you need another category theory construct to do it in. You could use rel, that's another type of category construction, which is very similar to the relation in a relational database, but that's really categorification, not really using category theory to its full potential. Whereas this is, but I agree, it's got a learning curve.
Yeah. Can you say a little bit more on the practical, and this is a very interesting example, can you say a little bit more about how all of this machinery has actually been used in constructing blockchain?
No, because blockchain, they are completely, they're very secretive about it because it's a commercial application. I've got a bit on the monad, which I gleaned out of their YouTube presentations. But I would think it would be, whether they use a Topos structure like this, I don't know. It's very simple, the data structure in blockchain, because it's basically just, it might just be the bottom, that bottom level of the transaction. Might not be anything else at all. In which case, you could mock that up in Haskell in 10 minutes. So, but I'm thinking more if you're going to do a full database application, you would need rather more. Okay?
Are there other types of products besides Cartesian products that you mean?
Cartesian product.
Are there other types of products besides Cartesian?
Well, there are lots of different types of product, like tensor product, Cartesian product. Cartesian product is all possible pairs. So if you've got so that P times A in the context of D is all possible pairs of P times A with those selected that map to a particular transaction. So if you want to make this into a really super bank account transactions, you can put in companies, branches to add to the users, and you end up with 4 pullbacks like that. Now, I'm not preaching this as a way forward for everyone. You can see there are 10 pullbacks in that construction, which you can use for manipulating. But what I am showing is that category theory is not limited to just simple examples. You can do very complex data structures in it without breaking the rules or doing any great deal of work. So you can mock up a Topos structure which is very complicated. Okay? Yes, and there is this rule that data structuring pullbacks. Yeah, we'll go on to another area, which is the music one. Right, so let's get on to the music. Topos for music. Viewed as a communication of some manuscript by communicators. So we can think of it as containing a score, other intentions of composers and writers, and it includes various types of musical notations. And the communicators comprise performers, other aspects of performance. So that's the basic idea. So we can put up another pullback, and I'm taking a different approach here. This one, I'm going to do a more top-down approach. So I've called this E for our Topos. That's the manuscripts, that's the orchestra, and that's the delivery. So this is a pullback of manuscripts over orchestra in the context of the delivery. So there's a many-to-many relationship between manuscript and orchestra. Each manuscript can be performed by many orchestras. Each orchestra can perform many manuscripts. So delivery might be things like played at the festival hall on the 23rd of March at 7:30, something like that. This is the static side.
Each manuscript can be informed by many orchestras.
Sorry?
You said each manuscript
Can be performed by many orchestras.
performed.
Yeah, so it's fairly open. So there we've got the top level is the manuscript, then we've got delivery and the order, and this thing here is the relationship between them. So that will be pairs of manuscript and orchestra with a delivery added for the context, which will be unique.
I noticed that there are two, is that the union, the square union of two commutative diagrams? The top, the existential, and the for all at the bottom? Is that what, you know, like the triangle, the arrow going up, and then you have it like
Which arrow?
the M, the MX.
Oh, the eta there. Yeah, I'm not going to discuss those at the moment.
No, not the eta, the triangle. If you look at the triangle MX.
Oh, that one there?
No, just the draw a triangle like between. You see how it's two triangles?
Yes, there are two triangles. Yes.
Are they two commutative diagrams? The squares are.
No, well, you can view it that way, but really the whole square is taken as a commutative structure.
Oh, okay.
So if you go from there via M, project onto M, and then go to D, you'll get the same. This is the intersection. You get a collection of deliveries going that way, and then you get another. If you go this way, the deliveries you pick out there, if they intersect with the deliveries going that way, you have a performance.
Okay.
So
M and O are
if those two paths give the same result, that will be a delivery of a particular manuscript by a particular orchestra.
And the M and O are the common objects between
Yes.
those. Okay.
Yeah. So there are two paths there, and those paths have to be equal for the value to be put in M times O. That's a basic idea. Yeah. Okay. So then you can expand each of these nodes into further callbacks. And so this has got S category for score, C for composer, and then we've got V for variant there. It's of course a mistake to think that classical music is played to the same score regardless of any situations. Each performance is different, and the performers will annotate these scores before the performance in the final rehearsal with the conductor. So the variant is important. This will broaden the genre. So this one says we've got a score here, we've got variants there, and we've got composers there. So if that was Concerto number 2, say, by Brahms, then the composer might be Beethoven down there, or Brahms, and the variant might be some well-known variant, or it may be just some improvisation, or not some instructions on the night for the actual performance. So you can see there's a very strong pattern with these. You can draw them formulaically after a while. And you don't have to put all these arrows in. I'm sorry I put too many arrows in. The critical one is this one going to S and then following the iota through to V, and that one going through to C, and that one going through to V. So another very similar diagram. So that's an expansion of the manuscript to include variants. Orchestra could be assemblage, another word for orchestra perhaps. Then you have the role of a musician. N is a named musician. So you might have here Joe Brown and his role is violin 1 or something like that. So this gives the relationship between the orchestra and their members in the context of a role. So that's another decomposition. Delivery, now this is very physical orientated delivery, could be location, hall and time. So L is the location up there, that's the hall there. So it could be like Sage would be the location in Gateshead, and that would be hall 2, and then the time might be 8 o'clock or something like that. And we have this relationship that's on the higher diagram. So each of these nodes can be expanded using this formulaic approach. Yes, so the nodes in the top diagram here are pullbacks in their own right. So we've actually got recursive pullbacks, and we need to match across the various nests. There is a logic to match across the various levels, and the top level is effectively a pullback of pullbacks. So what I've done here is I've replaced S by the S times C pullback. These are really squares. So I've really got square pullback in there, square pullback in there, and this is the product of those. So you can build up very complex structures. That's the point I'm making. And it didn't take me, if you're familiar with the pullback construction, it doesn't take too long. So.
Since existential is a negative of the universal A.
Not a negative. Existential it works on single instances.
So it's not, this wouldn't be right? They wouldn't be somehow reflections of each other?
No.
That's not the same, what you mean in there?
No, I don't think so. No, I think the for all is the universal one, working on all the instances on the left-hand side.
Oh, okay, so then you're not saying that...
So the existential works on one,
right,
and the universal works on all.
Oh, so they're not in a sense of a negative negation relationship between each other?
No,
oh, okay.
No, there's no negation in category theory.
Oh.
So, okay, so that's the basic structure that we've got, and it could be a lot more complicated. The reason that I produce that as a topos is that if I've got an entity relationship diagram, I can't actually have a monad work on that, because a monad, like in Haskell, is assuming some categorical context. So, metaphysics, Whitehead, of course, is his process of reality is very much in on this. The activity can be very complex, and generally this transaction, which we're going to work on, is viewed as atomic, succeed or fail. So if you have a transaction, it either works or it doesn't. If you put in a transaction, like a bank transaction, intermediate results are not available to others. So you can't pull out a quick £1,000 once you've got a credit, and then you find it bounces. You're not allowed to get at the intermediate results. So there are various principles here, and in the end the results persist. In category theory and in transactions in the real world, we use these multiple cycles for a transaction. And typically we have GF, GF, GF. So if you take this left-hand category and you're going to run a transaction on it to produce a right-hand category, then you have a free functor F which takes it forward, and a underlying functor G which returns you to the initial category. All a functor is a mapping between categories. There's some safeguards, but it's basically a mapping between categories. And we have two units here associated with the adjunction. The thing about adjunction is, if it's very simple, it's just an equivalence relation, but it can be a lot more complicated. And when you go over from the left to the right, you may not come back to the same position in the starting category. And that is called, the difference is called the unit of adjunction. And if you start at the right and go over to the left and come back to the right, you come back to a different place, that is the co-unit of adjunction. So you're measuring the change on each side of the adjunction. So you have these three cycles. They're performed simultaneously. There, as Whitehead called it, a prehension. It's a snap, not each cycle in turn. So we use these multiple cycles. Failure in adjointness, if you go over to the right hand, you take a step forward. That's really what you're doing. One step along the process chain. If you get a failure in adjointness, the transaction's failed, communication is suspended, and restart is necessary at some convenient point, which means a rollback. In music, it becomes much more complicated, because you need to distinguish. Music, of course, is never played faithfully to anything. I mean, you might have an archetypal representation and there's a score, but in the end, whether it's wrong or not is quite a subtle point.
You certainly never have a rollback.
Well, that would mean the performer stopped. You're having rehearsals. It means the performance stops and you go back to some convenient bar and you start again. You'd never do that in a performance.
I've seen it done in a performance.
What?
I've seen it done in a performance.
I must have been so
Start the wrong note, the whole audience starts. She stopped, they went back, and then she continued.
Well, that's a failure of a journalist. Okay. So, monad is used in pure maths to represent a process, and it's used in functional programming language, Haskell language, monad, test class construction. Why it's called Haskell, this language, comes from Haskell B. Curry, who transformed functions through currying in the Lambda context, so they decided to use his name for it. Just in time. And the blockchain transaction system for Bitcoin, and more recently other finance houses, is using switching to monads via Haskell, at least for some purposes. I'll explain why in a bit. Right, so the monad doesn't have to be based on an adjunction where you've got this free functor pair of functors going forwards and backwards, but it often is. So you've got functor fx to y, gy to x, and g is called an endo functor as the category x is both source and target. So the starting point is the same as the finish. So t is gf and s is fg. So when you have a monad structure, you've basically got the 3 cycles, which is t cubed, mapping onto the 2 cycles t squared and the 1 cycle t, 3 cycles of t. And in Bitcoin, the monad is assumed to be zooming in on the process. So you're actually zooming in on the task in hand. The comonad, you're doing the opposite. You're going from gf squared to gf cubed. You've got 3 cycles of s, and you're considered to be zooming out. So those are the basic ideas. So how do you write a monad? You can write it as a 4-cell, like I've got at the bottom there, with E is the topos that you're operating on, this structure you've developed. T is the jointness. Eta is the unit of adjunction, which is a change in the left-hand category in 1 cycle. And mu is the multiplication, t squared to t. So you can use this monad. That's the monad. The comonad is the dual. I won't go into that in any more detail. And this is the interesting thing at the bottom, this backwards and forwards switching, when you're actually running the process forward 1 step. The monad structure looks forward with f and eta, and backwards with g and g epsilon f. And the comonad structure looks backwards initially with g and epsilon, and then forward with f. So you've got this quite a lot of interaction backwards and forwards as you go from the step. As you go forward, you're having to see where you're going, and you also got to see where you're coming from. That's the basic idea. Yes, that's we'll go in with that. So the operation on Topos is simple. It's just E to E, where looked at from the intentional level, and closure achieved as the type is preserved. But that's just 1 step. So you can't do a musical performance on 1 step. You have to do the composition. So when you've got the physical notation for the music, and the performers in the category are also in the topos. So we've got all the information on the topos side, and we now want to roll it forward over a number of processes. So a single monad comonad action will take the music forward 1 unit of performance, which could be a phrase or bar or some other time slice, and then you have to run this monad comonad structure repeatedly to actually play the piece.
Lessons by John Cage.
What is?
Sorry, it was a flippant remark. I said lessons by John Cage.
Okay, yeah. So you have this adjunction as you go forward, and backwards. And if a jointness holds over 3 cycles in this one step, eta measures the creativity of a step going forward, which is dialectic, and epsilon, more interestingly, measures the quality of the step looking back, which can be viewed as rhetoric. So we're not expecting in music that epsilon is going to be just a straightforward representation of either the score or some archetypal performance. It will always be different, and epsilon will record that difference. So you can think of epsilon to some extent as the entropy. It is, in fact that might be why it's called that, it is in effect a measure of the drift from the archetypal definition for the piece, which of course nobody ever plays to because you have expression, so that sort of thing. Yes, so I've got this resynchronization, as you say, that doesn't happen in real performances. Yes, you're going mad. Yes, discussing when performers playing, they say they confirm. They don't confirm the monad-comonad structure, but they do say that you are, like in any communication, at any one moment in time, you are looking back as to what you've just said, and you are looking forward, anticipating what you're going to say next. And my suggestion is that such experience is captured by the monad-comonad structure, with its forward-backward nature and inherent adjointness. At least it's the closest in category theory to claiming that real-world experience. And a musical work is referred to as a composition. It is indeed a composition of steps, so you are going along a long path. You can't play it in the wrong order, except, as you say, with 1 or 2 comedians.
Couldn't it be also a categorical simulation of time, the previous slide? Of the progression of time? That slide where you said about entropy, and could that be like an indicating progression of time? Categorical?
I think the entropy is more the departure from the script, if you like.
Oh, okay.
Yeah. Yes, so composition is a heaven feature in category theory, as Lou showed this morning. So composition in music and in category theory is used in the same way. You are composing the output from one step into the input of another step. So you're forming a long line. But we have a problem. Composability is the key to all of this. You've got to compose monads. In MacLean and Eilenberg, they didn't really anticipate this. They thought monads would be a nice single process, and you could leave it at that. But in banking with Bitcoin, they've used the composition, not like in music. They've used it for composing, say, 100 one banking transaction is composed 100 times, placed on different machines around the world, so that you have 100 copies of that transaction recorded. And that is one transaction, and if any fails for any reason, you might have to roll back a whole lot, but they try and avoid that. Some of the transactions in Bitcoin hang around for days, whilst they're waiting for someone to switch on their machine somewhere. Oh, it's gone. So these Bitcoin people wanted to compose monads, many monads, and you can read these Meredith sessions on YouTube to find out about blockchain. And this provides the semantics for that banking example I had earlier. So it's proving popular, this, although some people complain about the slowness of it all, but it's this compositionality that is the key to reliability. So how do we compose monads? Well, you think you would, if you've got a monad E, F, G, E, 3 monads, E, F, G, you would just compose them, G, F, E, or you would execute E endlessly. But there's a problem in the Eilenberg-MacLean category theory in that monads do not compose naturally. And this was found out quite a lot through the Haskell system. When they started implementing the monads, they found that it didn't work very well. And the reason for that was that MacLean hadn't really assumed that people would compose them. So what they have to do is to strengthen the monad for composability, as in the Cartesian monad with products. So this is very important for category theory. I think, besides the point I've made that things can get very complex, I'm sorry for that, but I want to show that you can handle complex things. You really need practical applications of the category theory to test it. And it's only through the Haskell programming language development that the MacLean-Eilenberg problem was revealed. And the solution has come from another pure mathematician, Clisby. So that's good. And so Clisby left it. The problem is that you've got A times TB in the MacLean monad, and you really should have, for composability purposes, the A included within the T. It's a distributivity problem. And so you apply this Clisby lift to a monad, and then you can compose them, and everything works well. So if you do it in Haskell, everything is fine.
Sometimes known as the slice category, isn't it?
That's what?
Sometimes known as the slice category.
Yes.
Yes.
Yes, you can do that, yes. So our monads in music will always be Cartesian. There was another problem with monads that if they just operated on simple sets, it didn't work very well in this composability. Any bar line in music, other than the really puerile, will be complex. It will involve chords, got different instruments as well.
Can you define what you mean by Cartesian in this?
Cartesian means a product. So it will be a product of a number of notes.
Oh.
Yeah, that's the basic idea. So if we're going to use these, so these Cartesian monads are strengthened by the Clisby lift, absolutely essential for composition purposes. So summary of progress, I've got about 2 minutes left. Topos has been established as data type of choice. Design with pasted pullbacks and recursive pullbacks is being explored. And the Doolittle diagrams at the bottom level provide intention extension. Monad can process the topos readily as a single step, but that's basically pointless for any real application. And a Cartesian monad requires the Clisby lift for multiple composition, which is available in Haskell, and the advent of monads in Haskell gives an experimental testbed, so which is good, I think, major step forward. And look forward. I don't pretend this is a very sophisticated music application. More contact with real musicians. Topos should be elaborated. Possibly it could be made a bit simpler by making it more general. And these Doolittle diagrams being further thought. Clarification of monad, co-monad role. I think we need to describe the process in more detail. Time jitter we've done some work on, where you get time drift during any type of real application, and obviously jitter occurs in musical performances because sometimes people shorten a bar a bit to add expression. So that's something that can be done. And understanding the dialect rhetoric balance, and then that will feed the knowledge into how to use category theory. A bit more plain. Well, thank you very much for listening. I'm sorry for the...
Just one question, comment.
It was more a comment than a question, so maybe you should go first.
I just had a quick question. Is this a reason why symbolic Prolog as a symbolic programming language failed?
Why do you think it failed?
Not failed, but I mean, why didn't it catch on? Because I don't hear a lot of people talking about symbolic.
Yeah, I think it's got a lot of limitations with its first order logic.
Yeah,
I would think so. Yeah.
Okay.